What's going on, people? Mr. Phillips here. Thank you for calling Verizon. How do you like my new headset? Isn't this cool? I got this rad microphone stick. Virtual baseline heat flow lab sheet. Virtual baseline heat flow lab sheet. Demo. Graphing, you're not going to have to graph on the follow-up, but you're going to need to know like what your graph should look like or how to set up a proper graph. You'll see. So here are my two data sets plotted on the same graph. It doesn't look too good. First of all, look how flat and sad those lines look. If we set new y-axis mins and maxes, would it effectively zoom in on the graph and make it more dramatic, make those flat curves steeper? Yes, of course they would. So let's do that. What would be a good new min, y-axis min for this plot? 70? There we go. That's better. All right, what would be a good new max? 80? Cool. Oh, look at our title. Our title is currently a question mark. What would be a good title for this graph? What would be a good title for it, given that our two variables being plotted are temperature on the y and time on the x? You have two good possibilities, options for a graph title here, given those two variables. I'm going to go with, I'm always a fan of y versus x. So in that case, what's our y variable? Yes, temperature. Versus, and our x variable then is time. So temperature versus time would be appropriate. Also, another possibility is the effect of, whenever you're doing the effect of, it's the kind of the opposite. It's the effect of x on y. So in this case, the effect of, what's our x variable here? It's time. The effect of time on temperature. And that has to make sense in your brain too, in your noodle. Because, does time affect temperature? Does temperature affect time? If temperature affected time, we would be living in one cool reality if, like, the temperature on the thermostat or on the thermometer, as it rose, like, time went faster, and as the temperature went down, time went backwards or slower. Yeah, that definitely doesn't happen. But that would be pretty neat. So, do we need minor grid lines? Do you think we could grab somebody off the street? Because people are always grabbing people off the streets. So, do I have a loose clippy? Yeah, this thing is flying around. You can't really see it, but it's a little clippy cover. Whatever. Maybe I kind of like it. Grab somebody off the street and say, hey, look, where's this data point on the x-axis? And they'd be like, I don't know. It's somewhere between 0 and 5. They wouldn't know because there are no minor grid lines on the x-axis, and there's this giant space between 0 and 5. You need to make your graph as precise as possible so you could really pinpoint those data points on your graph. Grid lines and ticks. You ever been bitten by a tick? I have multiple times. I'm a big huge fan of those ticks, Doink! And then switch this over to horizontal axis. If your majors are counting in 5, 0, 5, 10, 15, well, then make your minor count 4. So it's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it for the graph. Looks good, doesn't it? So anyway, about ticks. Yeah, I'm a big fan. Whenever you go to gently pull them out, people, the best way to remove a tick is grab some tweezers. We always take tweezers with us when we camp and hike and stuff. Tweezers, grab as close as you can to the mouth bits parts where it goes into your skin, and gently squeeze. Get a good grip on it, but don't squeeze too hard. You don't want to squish the thing, and then you get the head part like trapped in your skin. So you grab it gently and slowly pull. It'll pop out. Okay, don't pull too hard. Make sure you get close to the skin, because otherwise you'll pull off its body and leave its head behind in your skin. Okay, and whenever you remove it, keep it in a baggie. All right, keep it in a baggie with little teeny holes poked in it so it can stay alive. Because if you start developing you're not sure if you got Lyme disease or not, you have the tick, and you can take it to get the tick to get tested or something, so that see if it has Lyme's disease. Anyway, delta t's. First of all, what are the equations for calculating your delta t's? I already gave you the delta TH equation in terms of the variables. THF minus THI. Do you know what each of those stands for? Temperature, heating, final. THI is temperature, heating, initial. Heating lasts from 0 minutes to how many minutes? When does heating stop? Yes, 10 minutes. Heating goes from 0 to 10. The temperature at 0, okay, what would that be? That's THI, temperature, heating, initial, or initial heating temperature. The temperatures at 10 minutes, what temperature would that be in terms of variables? THF, final heating temperature. Okay, so heating occurs from 0 to 10 minutes. All right, delta TC, cooling temperature changes. What are the variables for that? Well, it's still going to be final minus initial, but instead of THF, temperature heating final, it's going to be temperature cooling final, TCF minus temperature cooling initial, TCI. All right, and the same thing over here. Slurp. All right. So yeah, cooling goes from 10 minutes is when it starts, because right at 10 minutes, it goes from heating into cooling. So right at the 10-minute mark is when the temperature is recorded and the lamp is unplugged or turned off at the same time. So it seamlessly transitions from heating into cooling. So at 10 minutes, that is both the final heating and the initial cooling. All right. So I should probably switch this like blue for cool. Just so cool. So cool. All right, TCI, temperature cooling initial at 10 minutes. And then you cool down. So cool, feel the chill. TCI, you cool down for 10 minutes. From 10 minutes to 20 is cooling. So at 20 minutes, that's your final cooling temperature, TCF. And net. People are wondering, like, people miss the boat on net. They're like, wait, Mr. Phillips, what's a net? Is that, what, do we get nets? Net is another word for overall. If your house starts at 70, goes up to 100, and then drops back down to 70, overall, there is no change because you started at 70 and ended at 70. It doesn't matter if you could start at 70, go to 1,000,000 degrees, and then go back down to 70. The net temperature change is 0. To find net, you take your very last temperature minus your very first temperature. The very last temperature is your final cooling, TCF, right? That's the very last temperature. And the very first temperature was, in terms of variables, THI, the initial heating temperature. So net is actually TCF minus THI, your very last temperature minus your very first. I got a green. I did it. Is my thing still on? Uh-oh. 78 THF minus 72 is your THI. All right, 78 minus 72. I got a green. 78 minus 72 is 6. Wow, I got it. I'm good. You know what? I'm going to break this up into 2 parts because I'm afraid my microphone isn't working anymore and I don't want to waste any more time. Hi, welcome to Starbucks. What can we get started for you today? I'm bouncing back to net because it seems like, yeah, people were getting hung up on it. So net is an overall change. Okay, net is about the overall change in temperature of the house, right? If it starts at 72 and finishes, say, at 74, okay, this is the net. All right, that change is the net change, the overall change. If it starts at 72, ends at 74, then its net change is only 2 degrees Fahrenheit. If a house starts at 72, goes up to 1 trillion degrees, and then comes back down to 72, and the net is 0. And this temperature here, the very last temperature, remember, is the final cooling temperature, TCF. All right, and the very first temperature is the very first heating temperature, THI. So it's TCF minus THI. Snag-a-lag. minus 72.
Well, I did it again.
Net change for the small home of 1 degree Fahrenheit. For the large home, net temperature change of 2. Goals. What are your goals, man? You're reaching your goals. You're reaching for the stars. What climate did you choose? I don't know. Let's pretend we're a hot climate first. So hot climate people are trying to, what are you trying to do during heating? Whenever your house is being heated up in a hot climate, if you're in a desert and you're under the scorching hot sun, you're trying to minimize your heating temperature change. If you're in a hot climate and this is what your temperature does once it's being subjected to heat, if it shoots up, okay, to 200 degrees, that's not good. You're going to die. You want the opposite of that, okay? You want to minimize your heating temperature change. So if you're starting at 72, all right, ideally, here's what your temperature should look like throughout heating. All right, it stays flat line. So it starts 72 and ends at 72, and that's a heating temperature change of 0. That's ideal. Okay, so you're trying to minimize heating temperature change. All right, cooling. Whatever heat that a hot climate home gains needs to be lost. So you're trying to maximize cooling temperature change. All right, and then overall, well, if you pretty much start at 72 and you stay at 72 the entire time through heating and cooling, there is no net change. You started at 72, ended at 72, net change is 0. That's ideal for a hot climate. Net temperature change is 0. So you're trying to minimize your net temperature change, trying to make it as small as possible, as close to 0 as possible. Minimize heating, maximize cooling, minimize net. Cold climate people, it's kind of the opposite. Imagine you're in the Arctic. I'm in the Arctic Circle. It's about survival, people. And your house starts at 72. Somehow it's 72 degrees in the Arctic. During heating, you want to gain as much heat as possible. You want to, okay, you want to maximize your heating temperature change. You want to get toasty. You want to get toasty. You want to get warm. Welcome to Breakfast Toasties. Shout out to my homeroom people. Somebody at my door. And then during cooling, say if you're in the Arctic Circle, you know, you gain all this heat and the lights go out. It's nighttime. Do you want to lose all that heat? Do you want to freeze through the night? No. You want to keep all of that heat that you gained. All right. So during cooling, once you enter into cooling, you want it to flatline. All right. So there's no cooling temperature change. You maintain your temperature that you gained during heating. So you're trying to minimize cooling temperature change. All right. If you do those two things in a cold climate, if you do those two things, if you maximize heating and minimize cooling, look at the net. By the end of it, the net temperature change is massive. Okay. That's the goal. You're trying to maximize your net temperature change. Cold climate, you want to finish the whole test of the home, heating and cooling, you want to finish with the highest temperature possible. Hot climates, you're the opposite. You want to finish with the lowest temperature possible. Which house performed better? To look at your delta T's, people, in order to form conclusions. Remember, science is about it's about evidence-based conclusions. Which house performed better, small or large, for each phase of testing, heating, cooling, net? Hot climate, remember, we're trying to minimize heating, so we're looking for the home with a lower heating temperature change. The small home went up 6, the large home went up only 3. Okay, well, what house would you rather be in if you're in a hot climate in the desert? Would you rather be in the house that heats up more or the one that heats up less? The home that heats up less, the large homes. How do we know? Well, we looked at the delta T's, the temperature changes. You can't just say, like, Mr. Phillips, the large home did better, okay, in heating, all right? Just leave me alone. I want to be in my room listening to punk rock because I'm a teenager. Anyway, no, it doesn't work. That's not good science. Evidence-based, data-based, evidence-based conclusions, people. You know, because you compared the delta T's. Cooling. technically the small home did a better job there. It lost more heat. It lost 5 degrees, and the large home lost only 1. Small home did better there. Net temperature change in a hot climate. Remember, your goal net is to minimize it in a hot climate. Okay. Ideally, you want a net temperature. The best net temperature change you can have in a hot climate is 0. So which house got closer to that? Which house heated up less overall? The small home went up overall by only 1 degree, and the large home went up by 2. Did you guys hear that? Cold climate, during heating, your goal is to maximize it. So you're looking for the house with a higher delta TH. Which house gained more heat? Because that's what you want if you're living in the Arctic. Well, the small home gained more heat. It gained 6 degrees Fahrenheit, whereas the large home gained only 3. Cooling. The house that lost less heat is the house that did better during cooling. The large home lost only 1 degree, whereas the small home lost 5. So in this case, in a cold climate, the large home did better. Overall, remember, in a cold climate, you want to maximize heating, minimize cooling, all right, and gain as much heat by the end of it as possible. You want as high a delta T net as possible. So which house had a higher delta T net? The large home went up by the end of things, when all is said and done, went up by 2. The small home went up gained only 1 degree in the whole test. So the winner is large home. Use your delta T's, people. Use them as evidence. That's what science is. Okay, the process of answering questions with data, evidence-based solutions. It's a wrap.